to the second session of real analysis. In this session, we can discuss a few problems on principle of mathematical induction. The first problem is, prove that for each n element of n or natural numbers, the sum of the first n natural numbers is 1 plus 2 plus 3 plus etc. up to n is equal to n into n plus 1 upon 2. Let us look at the solution. We know the principle of mathematical induction. The first case is we have to show that P of 1 is true. So, given question is 1 plus 2 plus 3 plus etc. up to n is equal to n into n plus 1 upon 2. So, P of 1 means we have to consider the case for n equal to 1. So, for n equal to 1, look at the left hand side, LHS becomes 1 plus 2 plus etc. up to 1. So, it can be only 1 on the LHS. So, LHS is 1, whereas RHS will be equal to n into n plus 1 upon 2. On simplification, you will get 1 into 1 plus 1 upon 2, which becomes 1 into 2 upon 2, which is again equal to 1. So, we can see that the LHS is equal to the RHS. So, P of 1 is true, we have proved. Now, consider the second case, P of k is true. So, assume P of k is true. So, what do we have? 1 plus 2 plus etc. up to the number k is equal to k into k plus 1 upon 2. K into k plus 1 upon 2. Then consider, so we are assuming that this is true for the case k. Now consider 1 plus 2 plus etc. up to k plus 1. So, just before k plus 1 we have the natural number k. So, this can be rewritten as 1 plus 2 plus etc. up to k added with k plus 1. So, this is equal to, by our assumption or by the hypothesis of mathematical induction, we have 1 plus 2 plus etc. up to k is nothing but k into k plus 1 upon 2. So, we can replace this sum by k times k plus 1 upon 2 added with k plus 1, so that k plus 1 is common. We can take it outside, which is equal to k plus 1 into k plus 2 upon 2. That is taking k plus 1 common outside and taking the LCM, you are having k plus 2 divided by 2. So, that is same as k plus 1 into k plus 1 plus 1 upon 2, which is same as the question 1 plus 2 plus etc. up to n is equal to n into n plus 1 upon 2. Therefore, P of k plus 1 is also true, and hence by mathematical induction P of n is true for every natural number n. So, this completes the first question. Now, we can move on to the next problem. The second question is, prove that for each natural number, the sum of the squares of the first n natural numbers 1 square plus 2 square plus etc. up to n square is nothing but n into n plus 1 into 2n plus 1 upon 6. So, we shall look at the question once more. We have to prove the result 1 square plus 2 square plus etc. up to n square is equal to n into n plus 1 into 2n plus 1 upon 6. So, again first we take the case for n equal to 1. First case we have n equal to 1 in order to show that p of 1 is true. So, we consider LHS is equal to 1 square, which is equal to 1, RHS is equal to 1 into 1 plus 1 into 2 plus 1 upon 6, which is nothing but 1 into 2 into 3 upon 6, which gives you 1 itself. So, we can see that the LHS is equal to the RHS in this case. Therefore, P of 1 is true. The next case, we assume that P of k is true. Assume P of k is true. That is 1 square plus 2 square plus etc. up to k square is equal to k into k plus 1 into 2k plus 1 whole upon 6. So, we assume that P of k is true. Then consider the sum of squares up to k plus 1 the whole square. So, before k plus 1 the whole square you have k square. So, as we have done in the previous example, we will replace this summation by the right hand side k into k plus 1 into 2k plus 1 upon 6 plus k plus 1 the whole square. And that on simplification gives k into k plus 1 into 2k plus 1 upon 6 plus k plus 1 the whole square is nothing but k plus 1 into, when you simplify you will get 2k square plus k plus 6k, that means 7k plus 1 whole divided by 6. When you take the LCM you will be getting 6 whole divided by 6. So, that on simplification or factorization of 2k square plus 7k plus 6 gives k plus 1 into 2k plus 3 into k plus 2 upon 6. Now, when we write these two factors in terms of k plus 1, this is equal to k plus 1 into k plus 1 plus 1 into 2 into k plus 1 plus 1 whole divided by 6, which is exactly same as the result that we required. Therefore, P of k plus 1 is also true. And hence by induction we have P of n is true for every natural number n. So, that completes the second problem. Then the third question is to establish the inequality 2 power n is less than or equal to n plus 1 factorial. Again we apply the induction hypothesis here. Once again the inequality is, we will be writing the inequality 2 power n is less than or equal to n plus 1 factorial. 2 power n less than or equal to n plus 1 factorial. So, case 1 p of 1, or the case when n is equal to 1, we consider LHS is equal to 2 power 1, which is equal to 2, RHS is equal to 1 plus 1 factorial, which becomes 2 factorial, which is equal to 2. So, we can see that the LHS is equal to RHS for the first case. That means P of 1 is true. Now, consider P of k is true. Therefore, we assume that P of k is true. That is, we have 2 power k is less than or equal to, 2 power k is less than or equal to k plus 1 factorial. We are assuming that this is true for some natural number k. Then consider 2 power k plus 1, which can be written in the form 2 power k times 2. Now, we have already assumed that 2 power k is less than or equal to k plus 1 factorial using the induction hypothesis. And so, we can replace this 2 power k by the inequality. This 2 remains as such into k plus 1 factorial. But remember that our problem was 2 power n is less than or equal to n plus 1 factorial for every natural number n. So, what we intend to prove in this case is the result that we require is 2 power k plus 1 is less than or equal to k plus 1 plus 1, that means k plus 2 factorial. But now we have reached at a stage where 2 power k plus 1 is less than or equal to 2 into k plus 1 factorial. So, we can compare the result that we have obtained now with the result that we want to prove, and so we can have 2 and k plus 2 here. So, this is actually k plus 2 into k plus 1 factorial. So, we need to compare only the two numbers 2 and k plus 2 and see which is larger. So, we can see that 2 is smaller than k plus 2, and so we have this is less than k plus 2 times k plus 1. Because we are playing with inequalities, we can replace the 2 by a larger number k plus 2, so that the right side term becomes much more larger than this. So, the inequality is retained as such. So, 2 power k plus 1 is less than k plus 2 into k plus 1 factorial, that is 2 power k plus 1 is less than k plus 2 factorial as we wish to establish. And so, P of k plus 1 is also true, and therefore, 2 power n is less than or equal to n plus 1 factorial. So, that was the third example. Now, we shall look at the fourth one. Prove that 5 power 2n minus 1 is divisible by 8 for every natural number n. So, the question we will write once more: 5 power 2n minus 1 is divisible by 8. 5 power 2n minus 1 is divisible by 8 means 8 divides this number, or this is a multiple of 8. This is what we are going to establish for every natural number n. So, again the first case is for n equal to 1. For n equal to 1, this number on the left hand side becomes 5 power 2 minus 1. As we all know, 5 square is 25. So, this is 25 minus 1, which is equal to 24, which is equal to a multiple of 8. So, the case is established for n equal to 1. Therefore, P of 1 is true. Now consider or assume the second hypothetical condition for mathematical induction. We assume that P of k is true. That is 5 power 2k minus 1 is a multiple of 8. Now, we have to establish that 5 power 2 into k plus 1 minus 1 is also a multiple of 8. So, consider 5 power 2 into k plus 1 minus 1. So, that is equal to 5 power 2k into 5 square minus 1. Now, what we have in our hypothesis is 5 power 2k minus 1 is a multiple of 8. This we already established, this we have in our hypothesis. So, using this we are going to show that this is also a multiple of 8. So, what we have to do is we have to do a small trick here. We have 5 power 2k into 25. So, this is 5 power 2k into 25. Now, you try to write this 1 in terms of 25. So, 25, how can we get 1 from 25? We have to subtract 24 from 25, then we will be getting 1. So, now we have 5 power 2k into 25 minus 25 plus 24 as the initial expression. So, we can take 25 outside, you will be getting 5 power 2k minus 1 plus 24. By induction hypothesis, this is a multiple of 8 plus 24 obviously is 8 into 3. So, as a whole this becomes another multiple of 8. So, we have proved that the case for k plus 1 is also true in the case of induction. Therefore, P of k plus 1 is true. We have showed. Hence, the result is true for every natural number n. So, that was this example. Now, we move on to the fifth one. We have to establish the inequality 2 power n is greater than 2n plus 1 for n greater than or equal to 3. So, this is the second version of principle of mathematical induction that we will be applying in this case. So, you have to consider the inequality that we are going to establish is 2 power n is greater than 2n plus 1 for n greater than or equal to 3. So, we will write the equation inequality that we want to establish. 2 power n is greater than 2n plus 1 for n greater than or equal to 3. So, the principle of mathematical induction second version is defined for P of n naught, n greater than or equal to some natural number n naught. So, the first case that we have to prove is not P of 1, we have to show that this is true for the case n equal to n naught. That means, the first case is the case when n equal to 3. So, consider the LHS which is equal to 2 cube, the RHS is equal to 2 into 3 plus 1, and we know the LHS 2 cube is nothing but 8, whereas the RHS is nothing but 7. So, 8 is greater than 7 and therefore, the result is true for the case n equal to 3. Now, consider the second assumption, that is P of k is true for k any natural number greater than 3. for some natural number k greater than 3. That is 2 power k is greater than 2k plus 1. Now, with this assumption, we are going to establish the case of k plus 1. So, consider 2 power k plus 1, which can be rewritten as we have done in the previous case, 2 power k into 2. Now, 2 power k, we have already established that this is greater than 2k plus 1. So, this is greater than 2k plus 1 into 2. That is greater than, when you multiply 2, you will be getting 4k plus 2. But look at the result that we wanted to establish. We wanted to establish 2 power k plus 1 is greater than twice k plus 1 plus 1. So, we needed to establish this result. 2 power k plus 1 is greater than 2k plus 3 only. But now we have 2 power k plus 1 is greater than 4k plus 2. So, this was our aim, we have reached at this step. Now, as in the previous case, we need to compare 4k plus 2 and 2k plus 3. Compare these two for a natural number k greater than 3. So, which is the largest number? 4k plus 2 is greater than 2k plus 3, obviously, for any natural number k greater than 3. So, we can simply replace this with a smaller number 2k plus 3 on the right side. There is no change in the inequality, and therefore, we have established that P of k plus 1 is true. Hence, P of n is true for every n greater than or equal to 3 is established. So, that is a solution of this problem. Now, we move on to the next question, which is a similar one using the principle of mathematical induction. Second version, we will be proving this. We have to establish the inequality 2 power n is less than n factorial for n greater than or equal to 4. So, we consider the case P of 4 first. So, we are going to establish the relation 2 power n is less than n factorial. So, we can see that the case for n equal to 1, 2 and 3 are wrong here. That is why we are starting with the case P of 4. Suppose you want to put n equal to 1. Let us see what happens to the inequality. The LHS becomes 2 and the RHS becomes 1. Whereas, the case for n equal to 2, the LHS becomes 4, the RHS becomes 2. So, we can see that this inequality is actually reversed for the cases n equal to 1, 2 as well as 3, you can see. But for n equal to 4, we consider P of 4. P of 4 is the case for n equal to 4. We take the LHS is equal to 2 power 4, which is equal to 16, whereas RHS is equal to 4 factorial, which is equal to 24. So, we can see that the inequality is less than there. So, 16 is less than 24, and so P of 4 is true. Therefore, P of 4 is true. Now, we consider the induction hypothesis. P of k is true for some k greater than 4. That is, 2 power k is less than k factorial. We consider for some natural number k greater than 4. Consider the case 2 power k plus 1, which is equal to 2 power k into 2, which is less than k factorial into 2. And as we have seen in the previous example, 2 is a number which is less than k plus 1, because k is greater than 4. When you compare 2 and k plus 1, we can see 2 is less than k plus 1 for k greater than 4. Therefore, we can replace this 2 by a larger number on the right side. We will be getting k plus 1 into k factorial, which is nothing but k plus 1 factorial. So, we have established that the result is true for k plus 1 also, and hence the result is true for every natural number n greater than 4. So, we have established the case is true for any natural number n greater than 4. That is the inequality 2 power n is less than n factorial for n greater than or equal to 4. So, we have seen some examples of principle of mathematical induction. Many more examples are seen in literature. Thank you.